Yeah. Now let's see, everybody. See, isomerism is a word that is used when you have two molecules of same formula but start showing some different properties. Now, this can be categorized into two types of isomers. One is called structural or also known as constitutional. The other one is stereoisomerism. Within structural isomerism, we have various kind, which is chain, functional, positional, metamers, tautomers, ring chain isomers. While in stereoisomerism, again we have configurational and conformational. Configurational again has categorized into two forms, optical isomers and geometrical isomers. Okay. So as I said, this part is more interesting and we need to spend a lot of time. This part is easier. So let's try to figure it out how to identify the structural isomers today. For identification of isomers and how they are related, you always need to go and judge one important factor, that is degree of unsaturation. If you may recall, we have done this case earlier during IUPAC. I told you that degree of unsaturation or index of hydrogen deficiency tries to give a point of view whether how much number of hydrogens are required to make an unsaturated bonds into saturated bonds. For instance, if you have one pi bond, it implies that I require one hydrogen. If you have three pi bonds and a ring structure, to make it flat and plain here, I mean straight chain here, we require four number of hydrogens. So that number which you are writing is what we call it as the degree of unsaturation or index of hydrogen deficiency, or another equivalent DBE. One second. Yeah. By the way, all these terms are one and the same. Check it out. For example, here, check out this case. In this case, what did we notice? We have three rings here. So you can see ring 1, ring 2, ring 3. Three rings. How many pi bonds? 1, 2, 3, 4, 5, 6, 7, 7 pi bonds. So that makes it 10. So degree of unsaturation is 10. Now here if you notice, there is ring 1. Number of pi bonds 1, 2, 3, 4, 5, 6. 6 pi bonds. One ring. And this oxygen will also like to take one H plus. This oxygen will also like to take one H plus to convert into neutral form. So even if you have a charge also, we can convert, I mean, we can add an hydrogen to it. Hence, that should also be considered for degree of unsaturation. So total, what is the degree of unsaturation here? 8. Okay. Check out a similar case here. You can have NO2. I mean, two ring structures, right? So that makes it 2. Number of pi bonds are 12. Now this O minus can take one H plus, so that makes it half. So 14.5 is the degree of unsaturation. Okay. Now this compound is called cubane. For cubane, how do we figure out degree of unsaturation? You simply start breaking the bonds till the time it becomes a straight chain. So how many bonds I need to break? Check out 1, 2, 3, 4, and 5. If you break it now, notice this one. It is all straight chain now. Can you see this is all on one particular line only? So this is a straight chain. So how many bonds I have broken? 5 bonds. So number of bonds you're breaking in the cyclic structure, that becomes its degree of unsaturation. Same logic here. So we have 1, 2, 3, 4, 5, 6. 6 cycles I broke. And one big cycle will be remaining at the periphery. So break that. So how many? 6 plus 1, 7. Got it? Same way you can see here, one, two, three, four, five, six. Six I broke. One bigger cycle will be there. That will make it degree of unsaturation as 7. Okay. Now, if you want to calculate the dB based on a molecular formula, if the molecular formula is given, then what you would check is this formula here. That is number of carbons plus 1 minus number of hydrogens, halogens and nitrogens minus nitrogen by 2. So this gives the appropriate degree of unsaturation. Got it? So any molecule is given, you should be able to figure out this degree of unsaturation. Okay. Now, if you see the basic definitions here, you will notice that isomerism is compounds having same molecular formula but different physical or chemical properties. When we use the word structural isomers, we are referring to different structures but having the same molecular formula. What do you mean by different structures? Notice this example. I have N-pentane and this is called isopentane. You notice one thing, to convert N-pentane to isopentane, you require significant amount of energy, which means you have to break this carbon-carbon bond, take this methyl group, bring it to the new position and again arrange there. So typically in structural isomers, you will see one pattern. The pattern is bond breaking and bond making happens at two different locations. Clear? That is a pattern you need to identify to differentiate structural versus stereo. So in structural isomers, bond breaking and bond making both are happening at two different locations. While in stereo, bond breaking and bond making happens at the same location. Okay. So there, and the way to justify is the basic IUPAC name which you write. The IUPAC name must be different if it is structural isomers. Okay. Right, everybody. Right. Now notice which within structural isomers we have chain isomers. Chain isomers are also called as nuclear or skeleton isomerism. Here it will have different chain lengths. If you compare a parent or a side chain, it will have a different chain length. Notice 4 or more carbons should be present to showcase a chain isomerism. Okay, everybody. So it is very simple. If the chain length or writing IUPAC name, you have a different root wording. That means they are chain isomers. Positional. Positional or position isomerism is having same molecular formula. You have same chain length, both parent and side chain, but position of the same functional group should be at different locations. Like here, this is N-pentane, this is isopentane, and this is neopentane. And see, AB, AC, and BC. These three are chain isomers. Okay, this is a common name, by the way. When you write the IUPAC name, what do we write it here? It is 1, 2, 3, 4, 5. It is pentane. 1, 2, 3, 4. This is 2-methyl butane. This is 1, 2, 3. It is 2, 2 dimethyl propane. So names are different. IUPAC names are different. Hence they are chain isomers. Next, you see, same. Here this is P, Q and R. I have one chlorine substitution. but the chain length is different. Now it doesn't matter where the chlorine is, whether it is at position 1, position 2, 3, 4, it doesn't matter. As long as the chain length has been changed. The chain length has been changed means that itself is becoming chain isomers. You will not see anything with respect to the position of chlorine. So it is, you can see, irrespective of the position of any other groups there. Okay. For example, check out in the first case. 1, 2, 3, 4. This is the length of the chain, including nitrile group. But now it is 1, 2, 3. This is the main chain. So chain length is changing. So it is chain isomers. Here you see all three has a same amount of root word. Root word is what? Hexa, hexa, I mean cyclohexa, cyclohexa, cyclohexa. Correct. But have you noticed something? The side groups are different here. See, A is ethyl. Here it is dimethyl. Even if there is a name change, okay, of the side chain, then also you consider it as a chain isomer. Therefore, A and B are chain isomers. A and C are chain isomers. But if you notice B and C, everything is same name wise. Name wise, if you see, everything is same. If you compare the B, what is the name for B? IUPAC name for B? It is 1, 1 dimethyl cyclohexane. And if you compare C, it is 1, 2. Is it just the positional difference? Correct. But if it comes to the side chain naming as well as the main chain naming, everything is same. So if that is same, you call it as positional isomers. And that's why B and C are positional isomers. Next, notice this example A, B, C. Here 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. This is straight chain. This is uh, uh, straight chain. This is cyclic. But one thing have you noticed? None of these three has same molecular formula. And isn't it the basic thing of learning about isomers? That the molecular formula should be same. Then only we can say there any kind of isomers actually existing. So therefore, since ABC does not have same molecular formula, all three are, you know, uh, all these three are not isomers of each other. Next, let's report this case now. A, B, C, D. If you compare these cases, check it out. A to B. Have you noticed here it is ethyl that has become methyl. So chain isomers. B and C, same problem. Here it is ethyl. Here these are all methyls, chain isomers. A and D, same problem. Here there are three methyls. Here there is one ethyl, chain isomers. A and C, this is ethyl methyl, ethyl methyl. Only the position is different. So position isomers. B and D, methyl, 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 methyl. So again, only positional difference. C and D, again chain isomers. Okay. So I'm hoping all of you have subscribed to the fact that when do we use the terminology chain isomers and when do we use it for positional isomerism. Okay. Now let's understand when do we use the term functional isomerism. Okay. See, if the compounds having same molecular formula but have a different functional group altogether. Okay, functional isomer itself is different. So functional isomers will always be the dominant isomerism which you need to showcase, despite the fact there might be a chain isomerism, positional isomer. You will ignore these things when there is a functional difference, and you will simply suggest it as a functional isomer. Alright, check it out. This is cyanide, this is isocyanide, or this is nitrile isonitrile. So that makes it functional isomers. This is carboxylic acid, this is ester, functional isomers. This is alcohol ethers, functional isomers. Aldehyde ketone, functional isomers. Now, this is very interesting. Check. Even if you have 1 degree, 2 degree, 3 degree amines, you might say, sir, all three are amines only, but they are different functional amines. 1 degree has a completely different nature of functionality than 2 degree, 3 degree. So even in the case of amines, 1, 2, 3 degrees are functional isomers. Next, two double bonds versus a triple bond. That is also a functional isomer because triple bond is a different function, double bond is a different function altogether. Last one, check out this one. If you have a double bond and then you have a cyclic structure, while comparing these two, right, it is actually a functional isomer because it is a straight chain and a cyclic chain. Cyclic and straight chains are two different functions, but there is a word that is given to it, that is ring chain isomers. So this functional isomer is given a name that is called ring chain isomers. Everybody clear? Right. Now notice, for example, if you were to draw all the structural isomers which are possible, how many structural isomers are possible? I'll just show you two, three cases. Notice C4H10, I can make only these two. See, how do you make sure that you know how many structural isomers you can get? The first logic is to figure out degree of unsaturation. See, degree of unsaturation in this case is 4 plus 1, number of carbons plus 1, minus number of hydrogens by 2, which is again making it as 0. Right? So degree of unsaturation is 0, which means I cannot make any double bond, triple bond, or a cyclic structure. Next, C4H8 means degree of unsaturation is 1. Now, one pi bond can be arranged in so many ways. You can see one here, one like this. One I can make a cyclic structure, one I can make a cyclic structure like this with one methyl group. So how many structural isomers I am getting? I am getting total of 5 different structural isomers. Next, C3H6, degree of unsaturation is 1. So these two are possible. If you have C5H10, how many are possible? 10 such kinds are possible. You can see these are 10 such kinds. Clear, everyone? Right. Okay. So this is a basic idea you need to have. Rest all of these questions, you need to start working out along with this particular assignment which I'll be uploading now. This one is a very, very interesting assignment where you will have all the questions, correct? Like how many number of isomerism cases of for all these such cases, correct? And individually also you'll be asked how many number of isomers in different cases. Okay. So this is one assignment which you need to attempt when you try it for structural isomers. All right. In fact, structural isomers also has metamers and tautomers that I'll discuss in the next class.